Most students are very intimidated by this unit because it's all physics. And it's really a specific part of physics, kinematics or motion. Now, I've changed this over the years, the 11 years that I've taught this class. I used to kind of include this throughout the entire first semester. I just never felt like students really understood what was going on. So I changed it up 2 years ago and made it its own unit. Pros and cons. I feel like students understand things better now. However, it didn't help you when you found yourself in physics class doing your kinematics unit, okay? A lot of students now say they understand things, but why didn't you teach it to me earlier? Because this would have really helped in physics. It's like, this is gonna help you understand stuff that you've already learned in physics. Maybe you have a better understanding of things, okay? And I even changed it this year compared to 2 years ago. So like, if you noticed on the homework videos, I only have one lesson up because like lesson 2, 3, and 4, I've restructured to make it easier for you guys to understand, okay? And I want us to keep one thing in our brains, all units, because this is all that's happening, this entire unit. All that's happening is a dude is on a number line, okay? That's it. This entire, and that's nice to know. And we just have one situation. A dude is on a number line. Now, our dude has a position on our number line. He could be located at a position of 5. He could be located at a position of 0. We call this the origin. You might want to write that. The origin. Now, that's not like 0, 0. That's just like his position 0 on the number line. This dude could have a negative position. That's okay. We say he's left of the origin. Cool? That's this entire unit is a dude on a number line. Now the dude will be moving. You probably remember from physics the term velocity. You know? And we probably remember from physics that you could have positive velocity, which means you're moving to the right. Or you could have negative velocity, which means you're moving to the left. That's what our dude's going to be doing. Moving to the right, moving to the left. You probably talked about things accelerating or speeding up. Well, our dude's going to be speeding up, slowing down. That's all he's doing. Moving back and forth. Cool? What's really important is to like get rid of graphs and like X's and Y's, okay? And to instead think of positions at time. This is what we are going to use for a position function. Now this is very confusing to students because of the X here. They're like, oh, don't X's go inside because you're used to like F of X. But now it's like X of T, Y. Well, like here, at a time of 0, my position is 2. This is what you would think of as a Y coordinate. But just don't think about X's or Y's anymore. Just think like at a specific time, this is where the dude is located. Okay? This is my position, this is my location. Got it? We'll also be looking at velocity, which will be V, makes sense. We'll be looking at acceleration, which is A. That makes sense. Now, typically our guy is just moving left and right on an x-axis. Our guy could be moving up and down on a y-axis, but it's still the same thing. It's just like he's moving left, he's moving right, he's not moving diagonally, he's not going like in curves or anything. It's just left and right or up and down. We're gonna pretty much like 95% of our questions will be just left and right. Okay, so this situation, all that's happening. Okay, and We could say our guy is moving to the left or moving to the right. Velocity is where we talk about movement, right? If you remember this in physics, I'm about to connect it to calculus, and then you're gonna be like, oh, okay, I got it. And it's like, oh, maybe this dude is located at a position of 2. Maybe it's at the 3rd second that his position's 2. Like, I'm just throwing this at you so that you know, like, at a stopwatch stop at the 3rd second, 3.00000, here is my position. But my dude is moving to the left, so I would say my velocity at this time would be some negative number. Okay. At time t equals 3 seconds, I have some negative value for velocity, which I'm going to translate as he's moving to the left. Why does negative velocity mean moving left right now? Probably in the past, it's just like, oh, that's what it is. But we'll see how, like, it makes sense with calculus. Maybe this guy goes to the left, he comes back, he's back at this position of 2. Maybe he's at the 5th second. He's at a position of 2. But maybe my velocity at this time is now positive because I've returned to this spot. And we'll think of this as moving right. We'll see why it's moving right. Okay. Now, I will show you what it would look like on a graph. Hopefully, it'll make some sense. Let's say my dude, after 3 seconds, is now, oh, that's bad. I don't want the numbers to be the same. Let's do the dude after 2 seconds is now at a position of -3. Okay, so the dude's gone to a position of -3. We could graph those points 2-dimensionally. But no longer are we talking about X's and Y's. It's important to move away from that. We now talk about a specific time. We'll have position. And if X of 0 is 2, it would look like this point on the graph. At time 0, my position is 2. At time 2 seconds, I end up at a position of -3. Cool? What's happening in between? You know, my guide's moving to the left, maybe consistently, maybe not. But you can see my position is decreasing. My position is getting to 0. So I will go through the origin. I'm getting to a position of -1, -2, -3 after 2 seconds. So it's not X's and Y's, it's times and position, okay? Now let's find the connection to calculus. Like, great, this semester, why is this going to be easier now than it was when I first did kinematics and physics? All right, well, I'm going to give you a situation. I got a dude, he's moving to the right. At t equals 0, his position is -3. At t equals 2, his position is now 5. Okay, tell your neighbors what happened. Give me some numerical values. Tell me what happened. What happened with the dude? Go ahead. Just random observations. Tell your neighbors. Oh, interesting. Some people jumped all the way to a spot that just seems natural. Most of you said he traveled 8 meters over the course of 2 seconds. Okay, maybe you just thought about that. Okay, I'm just going to go ahead and say he traveled 8 meters over the course of 2 seconds, and I'm going to divide that or simplify that fraction so I have a per 1 second value. And some people went right there. They said, oh, that'd be equivalent to 4 meters per second, or 4/1, 4 meters per 1 second, 4 meters per second. Now, you guys are familiar with this, hopefully, that's like a velocity. Don't worry about that. But what you don't realize is what you did to get that, and how then we can naturally connect this to calculus. How do we get this 8? Well, you found the distance between 5 and -3 to find like distances. You can subtract values. Here, to find the time that elapsed, you can do 2 minus 0. Maybe it's obvious that it's 2, but you can write 2 minus 0. And then what you realize is like, oh, I took my position at time 2, I subtracted my position at time 0, and then I did 2 minus 0. And then you're like, oh, that looks familiar. Okay, what is that formula? Tell your neighbors, what's that formula? The slope formula. This entire class is about slopes. This entire first semester was slope, right? What was another word we used for this kind of slope formula? An average rate of change. The average rate of change of position gave me an average velocity. The rates of change of position will be velocity. Average rate of change is what you think of as a slope of a secant. Okay, so rate of change of position gives us velocity. An average rate of change of position must give us an average velocity. Slope of a secant. Slope formula. What would give us an exact velocity or an instant velocity? Tell your neighbor. An instantaneous rate of change of position would give us an instant velocity. What's other words for instantaneous rate of change? You just said it. Tangent slope. Derivative. X prime is V. Now, that might seem like weird or like great, but like I'm going to show you how it's like, oh, cool. Yeah, that makes sense. First, I'm going to go back to my dude, and I'm going to show you this chart. This was earlier. I had my dude move around, okay? I was having him speed up, slow down. And I would like you to look at his position graph and his velocity graph, okay? And I'd like you to keep in mind, back in the day when we would have the graph of F and how we would sketch the graph of F prime. What would we look at? Slope, okay? Okay, position is increasing. I'm going from 0 to higher position. My slope of X is positive. I have a positive value right there. I then have a max position. A max position, my dude has stopped. He's changed direction. The derivative, F prime, would be 0. My velocity is 0. My position is decreasing. The derivative is negative. Velocity is negative. Well, if velocity is the same as X prime, if a derivative is negative, the original thing is decreasing. When velocity is negative, position decreasing, that's why I'm moving left. Position decreasing. If velocity is positive, my position's increasing, I'm moving to the right. My velocity is 0, I'm stopped. I am constant. There you go. V is x prime. F prime, we've done so much with that. We're going to be doing the same stuff that we've done already. It's going to be x prime. Cool? Here's another thing I'm going to show you. And this usually drives it home. Because you guys are used to physics, you're used to using a bunch of equations to answer motion problems, right? You guys remember these equations? Don't want to. Okay, so this is x of t. All right? And you had a bunch of like initial conditions that you had to plug in, like you had a number for initial position, you had a number for initial velocity. You know, A was usually gravity, you plugged in negative 9.8. You guys remember all that stuff? All right. Now, not once did your physics teacher say, hey, take the derivative, right? No? Well, I'm going to ask you to take the derivative of this. Now, we are now in t land. We are gone from y and x land. We are at time and position land. So I am now going to take derivatives with respect to t, which means the derivative of 5t will just be 5. I don't have to worry about like a dt dx or a dy dt. Cool? Is that okay? Okay, so like t's are now what we thought of as x's, but we kind of like just don't worry about x's anymore. If I took the derivative of t squared, the derivative of t squared is just 2t, like normal. Cool? All right, let's take the derivative of this. Okay, we got x sub I, which is just a number. So what's the derivative of a number always? 0. All right, so I'm going to start x prime here on the left equals 0 plus. Okay, vi is a number, it's another constant. So it's like, could be 5. And what's the derivative of like 5t? 5. So what's the derivative of vit? Vi, very good. All right, and now let's take the derivative of 1/2 at squared. Okay, the 2 comes down. The derivative of t squared is 2t. The 2 and the 1/2 go away. We're just left with at. No, a is a constant. A is a constant just like vi. What do we see? What do we see? That equation. You were given to it, but it turns out it was just its derivative. It's the rates of change. Isn't that incredible? It's crazy. Now, it turns out, same goes with velocity and acceleration, and then we're going to make the connection, and then it's going to be like, oh, wow, okay, cool. And you're going to realize that a bunch of these questions that I'm asking you, like, hey, what's our velocity? What's our acceleration? When are we moving left, moving right? When's the velocity decreasing? These questions that I'm about to ask you, you've already done these questions. You already know how to answer these questions. This is going to be simple. It's going to be a review of things. It's just going to look different. Okay, ready? Let's see velocity to acceleration. So now I'm going to be like speeding up. My velocity started at 1. My velocity is positive. My position's increasing. I'm moving to the right. Okay. So my velocity at time 0 is 1 meter per second. My velocity at time 2 is 11 meters per second. What happened? And now I'm just going to go and lead you to victory. I've increased my velocity 10 meters per second over the course of 2 seconds. That's meters per second divided by second. If I divided the 2 to make it on a per second basis, meters per second divided by seconds would give me meters per second squared. And we are familiar with this as being like an acceleration. You know, speeding up, slowing down. Actually, and I'm going to say this, and it might not make sense to you, but maybe later it does. Like, your understanding of acceleration before coming into this class messed you up when I talked about things decreasing at a decreasing rate, and decreasing at an increasing rate. But we'll get to that soon. How'd you get the 10 over the 2? You did a y2 minus a y1 over an x2 minus an x1. But I'm not going to say it's y's and x's. I'm going to say it's v's and t's. And what is this slope? The average rate of change of v. That gives me an average A. So what do we learn? The rate of change of V gives us A. I don't know how to write acceleration, so I usually just write Excel. Is it 1L or 2? Who knows? Anyways, 1. Sorry about that. So, rates of change, how quickly velocity is changing, gives us acceleration. Average rate of change, slope of a secant. Use the slope formula. Average rate of change of V will give us an average A. What will give me an exact A, an instant A? The derivative of V. And then we're about to blow the doors open. The instantaneous rate of change of V will give us an exact A. An instantaneous rate of change is the slope of a tangent. How do we find that? We take the derivative, we use the derivative. V prime equals A. Well, if V is X prime and A is V prime, what other connection can we make? Really? You said it. What was it? Yes. My friends, we'll go straight here. We are used to F. Then when you take the derivative, gets F prime. And when you take, and Morella, you are now, will be immortalized on YouTube for that answer. So great job. We're used to F prime to F double prime. Well, we think X, V, and A are just like 2, 3 different things. But we just discovered that X prime is V. We just discovered that V prime is A. Well, if X prime is V and V prime is A, X double prime is A. My friends, we are going to go back and essentially review Unit 3. And it's not the calculus of physics, it's the calculus of motion. There's a lot of other calculus applications in physics. And we're going to use our friend, the sign analysis. We're going to look at X prime. We're going to look at X double prime and its sign. But now we know that the derivative of position is velocity. Now, when we did this in the past with F prime, we'd say, okay, positive, negative, that would tell me that F, in this case X, is increasing or decreasing, right? But now I'm going to just go back to thinking about my dude. And I'm actually going to translate this a little bit differently. If X prime is positive, if the position is increasing, what's the dude doing? Yeah, very good. Now I say, oh, I'm going to the right on the x-axis. If X prime is negative, if my velocity is negative, if my position is decreasing, I'm going left. Now we used to go X double prime to X prime to X. We could do that, but it's actually best to just stop here. We'll be able to tell based on the sign of A when V is increasing and decreasing. And then with that and another analysis, we'll be able to tell about like speeding up, slowing down. It's like, it's all the same. It just looks different. And then we might want to go backwards. In the last unit that we just learned, we would take F double prime and we would turn it into an F prime and then we would turn it into an F. Well, we might have a situation where I'm given an acceleration equation. We know that's X double prime or V prime. And I want to turn that into X. Well, let's take the antiderivative. You'll get there. The antiderivative of A is V. The antiderivative of V is X. Cool. Okay. If I gave you these questions at the beginning of class, you'd have no idea what to do. But now we're able to translate things. We are given a position equation. Now, what is this telling me? Where my dude is located at certain times. I plug in T's, I get locations of the dudes. And you might think, oh, let's plug in 0, 1, 2, 3. No, 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 we're better than that. Because now we can quickly and easily find X prime. You just take the derivative. Okay, what's the derivative of X? Write it down. Nothing fancy, nothing crazy. What is it? Good. 3t squared minus 16. What do I have? B. I know I could take the derivative of my first derivative to get my second derivative. And I get 6t minus 6. What do I have? V prime, or A. And now questions like, what's the velocity at time equals 2? I'm going to skip the first one. We'll come back to them at the end. What's the velocity at time equals 2? I have no idea. What do I do? Well, literally, velocity is the same as x prime. What's x prime of 2? Oh, I have an equation for x prime. Just plug in 2. Ends up being 0. What's that mean? Yeah. X is constant. The dude's position is constant. The dude stops. Velocity 0. What's the acceleration at t equals 2? Gosh, this seems so complicated. Oh, so simple. Acceleration is the same as just the second derivative of position. I already have an acceleration formula. I found it because I know how to take derivatives. Okay, find the acceleration at time 2. Perfect. 6 times 2 minus 6. X double prime is 16 minus 6. We have that. 6. Now, meters per second, I don't know. What did I say? I didn't even tell you what it's in. So it's like, don't worry about units so much. Okay. Okay, cool. When has the particle stopped? When is the particle moving to the left? Let's start with those two. Two questions that actually I will answer 2 different ways. Well, I will answer using one thing. I'll answer both questions one way. That's what I meant to say. If I'm able to know the sign of x prime, I will know how position's increasing or decreasing, or I will know when I'm moving to the right or left. Guess what, guys? We'll break out our friend, take the derivative, set it equal to 0. Sign analysis. It's back. Yay! You guys missed it. I know you did. We've already taken the derivative. Let's set it equal to 0. And let's do a sign analysis. And then we'll be able to answer both of these questions. Boom, all at once. You got to find them all. I want to figure out, how's this dude moving? We took the derivative. It's 3t squared minus 6t. Set it equal to 0. You guys remember your friend Mr. Factor? Oh, we have our derivative set equal to 0. That'll find when the particle is stopped. We already found one of the values at 2, but another value is at 0. And when I do a sign analysis, I'll know when the particle is moving left and moving right. When position is increasing, x prime is positive, I'm moving to the right. When position is decreasing, x prime is negative, I'm moving to the left. That's it. All right, just check your answers with the neighbor. We're all good. Looks like we're all set. All right, fantastic. We remember to plug in test points into our factored form. It's easiest to do. We know that since we've found all of our zeros or undefined values, we found all of our possible sign change points. Boom. We found all of our zeros. So I know that all of my signs are going to be negative. Between 0 and 2, I'm going to be moving to the left for time values between 0 and 2. I have open brackets because I'm not including 0 and 2 because that's when my particles stop. Okay, next question. I need to figure out when velocity is decreasing. Tell your neighbors, what do you think you need to do?
Take the next level.
If you remember to tell when something's decreasing, you look at the sign of its derivative. Well, guess what? This is x prime. This is x double prime. We are going to do our friend x prime is decreasing when x double prime is negative. It's the same as what we've done before. But now we'll do a sign analysis of A, which is x double prime. X prime tells you about x double prime tells you about x prime, x v a, x prime, x double prime. You already have the formula for x double prime, which is a, 6t minus 6. Set it equal to 0, you get t equals 1. Plug in something like 2, we get positive a's. Plug in something like 0, you get negative a's. Or you can think of x double primes, x primes. I probably would want you to just stick to this for now, and then eventually change to A and B and just understand that they're the same. But to really drive home the point that this is not new, it just looks different, I'm going to keep the x primes and the x double primes so that you are like, oh yeah, this is familiar, we've done this before. Okay, now we'll talk about this origin question in a second. Let's go back to the average velocity, the average acceleration. It's just very important to realize, like, it's still a slope. Average v would be an average rate of change of x. And average a would be an average rate of change of v, not an instantaneous rate of change. So remember, with average rate of change, slope of the secant, slope formula. And I'm just going to set it up. I'm not going to spend the time to do it. This would be x of 2 minus x of 0 over 2 minus 0. And you'd have to plug in 2 and 0 into x to get positions. And then here, you'd have to plug in 0 and 2 into v. Okay? Now, a new type of question. And this is not a question that I asked you with f prime and f double prime, because it really is nicely worded with this motion. Question is, when is the particle moving toward the origin? I'm going to change it to, is the particle moving toward the origin at t equals 1? And this actually initiates other future questions we're going to see, where like, if you are looking at one time, don't bother doing full sign analysis for all time. We can just focus on what is my position at 1, what is my velocity at 1, what is my acceleration at 1, and then maybe figure that out. So I'm not going to look back on the sign analysis. But I got to understand, like, what must be true for my dude to be moving toward the origin. Okay, so tell your neighbors, and I'm just going to start playing this. Like, when is this dude moving toward the origin, where we consider the origin to be right here in the middle at 0? Okay, go ahead and talk about it. Okay, turns out it's not about acceleration. It doesn't matter about like what we'll talk about soon, speeding up or slowing down. It's about where he's located, and which direction that he's traveling in. If we have a positive position, but that position is decreasing, if the position is decreasing, the derivative is negative. Positive position, negative velocity, I'm going towards the origin. If you have a negative position that's decreasing, you're going from -2 to -2, you're going away. Negative position, positive velocity would be going towards the origin. Okay? So you got to look at position, and like if the signs are the same, position's positive and increasing, we're going away. If position is negative and decreasing, we're going away. The signs are opposite. So all you need to do is find where is he located and how is he moving. Okay? Answer the question. Is he moving toward the origin or away from the origin? Okay. I have the equation for x of 1. It's -2. Don't have to worry about the sign analysis, though. You already know that we're moving to the left at 1. So that might help. But it's easy enough to plug in 1 into V to get -3. My dude is located to the left of the origin. My dude's moving left. The velocity is negative. The position is decreasing. Okay? Now, we should be able to answer this question without graphing V and A. So I'm going to delete this really quick. Though we can. And actually, I don't want to spend too much time on this question because most of the time, for the remainder of the unit, you're given V. Okay? Every time. Like, rarely are you given X. Okay? But let's just do these anyways. This is the dude's position. Think about what we're always going to keep in our mind. A dude on a number line. I don't know where the dude's located. Like, don't assume that. Tell me, where does the dude start and how does the dude move? Okay? And if you can figure that out just by looking at this graph, then you have an understanding of like what we're doing here. And answering the questions, we don't really need calculus until the last question. The whole second to last question, the velocity increasing part. So tell your neighbors, like, what's going on with the dude on the number line by looking at this. Go. Here, I'll even give you some values here. This is 4, this is 3, this is -3. Okay. If you said the dude starts at a position 4 when time is 0, he then moves to the left, he gets to the origin at t equals 1, he keeps moving to the left till he gets to a minimum position of -3, he then goes back to the right till he gets back to 0 at t equals 3, so my stopwatch reads 3.000 here. He then moves to the right till he gets to a position of 3. Then he moves back to the left, going back through 0, ending back up at -3. Okay, answer the question. When's the particle stop? You can answer this without knowing calculus. Tell your neighbors, when's the particle stop? Or when's the dude stop? Good. 2 and 4. Because the slope, or x prime, is 0. Right? When's the dude going to the right? Now, you don't need to know calculus, but calculus will confirm our answer. When is the dude going to the right? Between 2 and 4, when x prime, which equals v, is increasing. Wait, no. When x prime, which equals v, is positive, that's when x is increasing. 2 to 4, I'm going from -3 all the way to 3. My slopes are positive. X prime, which is v, is positive. X is increasing. Okay, here comes the best question. Yeah. When is my velocity increasing? This is when calculus helps tremendously. Velocity, which is x prime, is increasing when x double prime is positive. That's when A is positive. That's when x is concave up. Now we can break this guy out, the whole concavity. And look, my friends, we are concave up. All here, 0 and 3. Okay, now, you might see a couple homework questions like this. But most of the questions will be given the graph of velocity. Okay, so let's go to one of those, and then we'll come back to the Unit 6 going backward questions. So skip the next 2 questions, boom. Most of your questions are now, from now on, hey, this is V. Okay. This V is x prime. This is like when I was given the graph of f prime. This is like our favorite Unit 3 question, where if we understood x prime, positive, negative, tells us x increasing, decreasing, x double prime, positive, negative, x prime, increasing, decreasing, that we'd be able to answer any of the questions that they asked us. When given the graph of f prime, when does f have a max? When given the graph of f prime, when is f increasing concave up? The questions were being answered given the graph of f prime, when does f have horizontal tangents? The questions we're answering, the exact same questions, they just look different. When is the particle moving to the left? You can either say, that's v negative. That's when my position is negative. My position's derivative is negative. That's when my position is decreasing. I go to this, and then I say, what do I have? And what's my answer? Tell your neighbors, what's the answer here? Boom. We have v. We have x prime. When is x prime negative? It's when the values of x prime are negative below the x-axis. That's between 2 and 4. Look at us. We're doing stuff we've already done. It just looks different. When does the particle stop? When v is 0, when x prime equals 0. I have v, when is it 0? It's not at 1 and at 3. It's at 0, at 2, at 4. Okay, now, let's see. When is the acceleration negative? Unbelievable. A is x double prime. When is A negative? Well, that's when x prime is decreasing. This is x prime. When is it decreasing? Between 1 and 3. It's the same questions we've answered. They just look different. You could also say, oh, it's when v prime is negative, and you can look at the slopes of the tangents of v. You know, it's up to you. There's different ways to think of it. Like, this is v prime. Okay? All right, great. That was, for the most part, Unit 3 repeated. Well, what about Unit 6? What about these whole antiderivatives? Do we do antiderivatives? Sure. Now we're going back. We're going back a page. Back a page at the bottom. Back a page at the bottom. What is the position of a particle at t equals 2 whose velocity via t is t squared? Its position at time t equals 3, x of 3 is 5. Well, I'm given x prime. I'm asked to find an x of 2. Go. You get the answer. Shout it out. I want to find x of 2. That is correct, Treant. You are now immortalized. Negative 4/3 is correct. Yeah, what? Oh, the C. Yeah, I remember about the C. When I take an antiderivative to go backwards, we know that we need to include a plus C, and I use an initial condition to find said C. Fantastic. X of 3 is 9 plus C, which equals 5. C is negative 4. Now I have, by going backwards, a formula for X. And I can plug 2 into this to get 8/3 minus 4, which is 8/3 minus 12/3, which is negative 4/3. All right. Do the next one on the next page. If only we knew about slopes, if we only knew about sign analysis when we took physics the first time, things might have been easier. Most of physics, it was like graph interpretation, and you didn't know like the connection between X and V, and it's just, yeah, it's just tough, and it's easier once you know calculus. Everybody get this one? I want the position at for 5 seconds. Nope. Now, ready? There's one problem, and this is new. Ready? This is new. Initial velocity and initial position. What do you think that can be translated into using like math notation? Yeah, VIXI. You know what? My position or my velocity at time 0 is 3. My initial position is my position at time 0. We're not going to use VI or XI because I don't have formulas for these things. I'll say at time 0, that's my initial. Okay? And that'll help you. That'll fix it. I should have said that before we started. Arnold, you got it. It's 44. We go from A to V to X. Find C along the way. Plug in 5. 25 plus 15 plus 4. We get 44. My dude's way off to the right. Cool. Okay, now, in the past, we would look at F prime and F double prime at the same time. Right? And I would ask you the following questions. Let's see if you can answer it. When is F decreasing at an increasing rate. Here's your sign analysis of F prime and F double prime. When is F decreasing at an increasing rate? Go ahead and try and answer that. Okay? Now, this is when it helps to have our arrows, right? F prime tells us F increasing or decreasing. F double prime tells us when F prime is increasing or decreasing. When is F decreasing? When F is going down. When is its rate increasing? When its rate is increasing. Okay? We would combine the two and then we'd be able to answer 0 to 1. We're about to finish off by talking about speed. And when is my dude on my number line speeding up or slowing down? And it was actually your kind of internal understanding about acceleration, speeding up, slowing down, that made some of you answer this incorrectly. Do you remember some people would think like F is decreasing at an increasing rate? What does that look like? A lot of people would say decreasing at an increasing rate looks like this, decreasing concave down. Right? Because you're decreasing and you're going faster downward. That's what you would think, right? That's because you actually naturally had an idea about acceleration. And you're like, you're speeding up. You're increasing, right? This is wrong. If F prime is negative, I'm going down. If F prime is increasing, F is concave up. Remember that? So decreasing at an increasing rate, not going down, concave up. And it's like, oh, because the slopes are increasing, right? Okay, cool. What I'm about to tell you is that like your natural instincts, before I like completely messed them up, would have helped you if I talked about speed questions, okay? Because we're about to talk about speeding up and speeding down and slowing down. And you'll see that if X prime and X double prime is like that, well, never mind, we'll just talk about it. Speed is the absolute value of velocity. It's velocity without direction. Okay, if your velocity at a specific time was negative, you'd say your speed, and I don't use another terminology for it, the speed at that time would be positive. Okay? Okay. Now, what is something speeding up? Tell your neighbors. You'll all be wrong. But tell your neighbors your initial instinct, and then I'll tell you you're wrong, fix it. You'll now think of it this way. Go. When is something speeding up? Yeah, right? Everybody says when the acceleration is positive. And they're wrong. So you're going to fix this. You're going to fix this misconception. Okay? I'm going to go back to my dude. And what I'm telling you is that you could be speeding up, but your acceleration could be negative. Okay? You could be speeding up and your acceleration could be negative. Ready? Let's go back to the beginning and watch. Okay, acceleration is positive, I'm speeding up. Okay, my acceleration is negative. I had slowed down, stopped, and now I'm speeding up. Okay, I'm slowing down, I've stopped. Okay, now I'm speeding up. My acceleration is positive. But now I'm slowing down, I've stopped. My acceleration is negative. The green arrow is the acceleration. Now I'm speeding up. Slowing down, stop, speeding up, slowing down, slowing down, slowing down, slowing down, stop. Speeding up, speeding up, speeding up. So I could be speeding up going to the left. I'm still speeding up right now. I could be speeding up to the right. What must be true? Not acceleration positive. Because if I have a negative velocity and that velocity is increasing, its derivative is positive, I'm going to be going from -4 to -3 to -2 to -1 to 0. I'm slowing down until I come to a stop. That was well timed. Okay? Now, if my velocity is positive and increasing, I'm going to the right and my velocity values are increasing. Here I am speeding up. But the same can happen if I have a negative acceleration. If I start with a positive velocity and I have a negative acceleration, I'm going to start by slowing down until my velocity gets to 0. So my velocities go from positive to less positive, my velocities are decreasing. And now we're going from negative to more negative. Okay? So what must be true to be speeding up? That's it. B and A have to have the same direction or sign. My velocity can be positive and increasing. My velocity could be negative and decreasing. To get that, we'll need x prime, and then we'll also need x double prime to be positive or negative. When am I going to be slowing down? B and A have opposite signs. Okay? All right, let's go back to this first equation we had for a position of my dude on my x-axis. T cubed minus 3t squared. And I'm asking you, when is the speed of the dude? We say particle, think of it as a dude on a number line, moving right and left. All you got to keep in your brain, all units. When is the speed of it increasing? Well, we need an analysis of x prime and x double prime to be looked at the same time. We actually already did this. We could do it again. So go ahead and do it again. You guys know how to do it? So do it again. Same as the first one. Good. Good. You're missing one interval. Yep. Great. Now, sometimes having this velocity decreasing, increasing is helpful. Sometimes it's not. Sometimes it's better to be like, when are my arrows going in the same direction? When is V and A going to have the same sign? I think it's easier that way to just identify negatives and negatives versus, okay, I'm moving to the right because V is positive, my position's increasing. I don't like to put position increasing anymore because it's helpful to just say I'm moving to the right, and then I'm moving to the left, and then I'm moving to the right. I'm moving to the right, but my velocity is decreasing, so that means like positive 5, 4, 3, 2, 1. I've stopped, I move to the left, but my velocity, like that sometimes can get confusing. So just look like what's going on. You know, one of the signs the same. There, there. Sometimes if we include like positives and increasing and decreasing and we keep that in our brains, it might be confusing. Okay. Signs of x prime and x double prime need to be the same. We need to be increasing concave up or decreasing concave down, and that is speeding up. Okay? All right. Here's a graph of V. When's the speed decreasing? When are we slowing down? Two ways to do it. You can do your full-on sign analysis, or you can think of your two situations where you could be slowing down. Slowing down is velocities of positive 5, 4, 3, 2, 1. Okay. Positive velocity that's decreasing, or negative velocity, negative 5, negative 4, negative 3, negative 2, negative 1. That's a negative velocity that's increasing. I mean, there's a lot of stuff going on. A lot. But these are my two options. When is velocity positive and decreasing? When is velocity negative and increasing? Positive and decreasing, negative and increasing. I heard a lot of physics students in the past, they stick with this answer that I believe they learned in physics because they had a lot of questions about speeding up and slowing down. And they'd always say, because velocity is going towards the x-axis, the t-axis. It's like, yeah, that's correct. Why? Positive velocity that's decreasing, or positive velocity, the slopes are negative. Negative velocity positive, that's one way to get the answer, is to go and just immediately think about that. The other way is to do the analysis of V and the analysis of A, which is V prime. Positives until 2, negatives until 4, positives after that. Oh, we still got 3 minutes. I'm not done yet. And then V prime, which is A, slopes of V, or V's direction. V's increasing until 1. V prime is positive until 1. V's decreasing until 3. V prime is negative. V's increasing after that. And then you can look at when are the signs opposite. 1 to 2, 3 to 4. Two ways to do it. Okay. Is the particle speeding up or slowing down at t equals pi over 9? We just did 2 questions in a row that involved like kind of full-on sign analysis. Since you have 1 point, just like we did with the going towards or away from the origin, do not do a full sign analysis. You're going to waste your time. All you need to know is what is your velocity at this time and what is your acceleration which is the derivative of velocity, at this time. You don't even have to know what the value is, as long as you know that it's positive or negative. Sine of 3 times pi over 9 turns into pi over 3. Sine of pi over 3 is root 3 over 2. That's positive. We need a formula for A. Somebody take the derivative of V, and you will become immortalized. Thank you, Triant. Twice in one class. Plug in pi over 9. Yeah, we got to be careful. We're going to go back and forth. This is also positive. We're speeding up. All right. This is the easiest one.
I know, but the first lessons are always the most confusing.
Because it's new.